So we've seen what the waves look like for the electron trapped on a wire. The first one looks like this. Here are the blocks that hold the wire down. Here's the wire. And if we pluck this, we'll get a wave that looks like this, and it will vibrate up and down like that. Now, they call this wave function, the shape of this, psi. They give you a symbol. Now, since n equals 1 for this, the quantum number is 1. Quantum number in this case is the number of peaks and troughs along the wire. They'll call this psi 1. This is the first wave function. It's the ground state wave function. And we've already seen that we can calculate the energy of the first state. And we did this already. L is the length of the wire. M is the mass of the electron. H is Planck's constant, and this is the energy of this. So each state that the electron can have will have a wave function associated with it and also an energy. But what does the wave function mean? The interpretation of the wave function is called the Born interpretation. The probability, we said this was a probability wave, remember? The probability of locating an electron at a specific point is equal to the square of the wave function at that point. So if I square the wave function, it shows me the probabilities of finding the electron at different places. If the electron were just a classical particle, I could tell where it's going to be spending most of its time. So here's my wave function psi 1. If I square it, if I take each value and I square it and then I plot that, maybe I'm going to get something like this. This is psi squared. And this shows me the probability of finding the particle at any given point. So it's most probable in the ground state that I am going to find the electron right here at the midpoint with this particular wave function, with psi 1 squared. So I can picture this as kind of the electron is spending most of its time here, less and less and less of its time as you go out. Let's see if I can get a better pen. So it's spending most of its time here, and then less and less and less time as you go out. And it spends absolutely no time at the nodes. The probability of the electron being located at the nodes is 0, because that's the value of psi squared at that point is 0 as well. Let's look at some of the other wave functions for the electron on a wire. Let's look at n equals 2. Here are the blocks that hold the wire down. Here's the wire, here's the wave. Now this time, to make n equals 2, I need a peak and a trough. So I'm going to put my finger there and then pluck the wire. And I'm going to get something that goes up and down here and up and down here. And I always have a 0 amplitude here at this node. So I've got 3 nodes here, 2 at the ends and 1 in the center. If I do psi squared, here I've got a positive amplitude, and here I've got a negative amplitude. So if I square this, it's going to look like this. Notice that if I'm squaring a negative number, I get a positive number, so it goes up. So this is what psi squared looks like, and this would be psi 2 squared, because n is 2 here, my energy is going to become 2 squared here, or 4. There'll be a 4 there. And this is psi 2 that I'm looking at here in purple. And this is psi 2 squared in red. So where's the electron going to be most likely to find? Where are you going to most likely find the electron? Wherever this function is the greatest. This is a likely spot for finding the electron. This is a likely spot. The probability of finding it goes down until it hits 0 at that node. Goes down until it hits 0 at this node. So you're most likely to find the electron at these 2 spots. Those are the most probable locations. And the least probable locations where the probability is 0 is at the nodes. And you can keep going and interpret the other wave functions that way. Now, what does this do for us? It gives us a way to see what electrons are doing, not just in atoms, but in molecules, because the electrons in molecules have also got wave functions. If I look at a water molecule, here's a oxygen nucleus here, and here's a hydrogen, here's the water molecule. Now, if I look at the square of the wave function, I'll get a map that shows me how the electron density changes. And there are contour lines that I will get. And these are like the contour lines that you see on a topographic map. And they show me how likely it is to find the electron. It is this. If this was a mountain, if you looked at it on this from the side, this would be the top of a mountain, and these would be 2 lower hills next to that. It is most likely that you're going to find the electron where the altitude on this topographic map is highest. So it's most likely that you're going to find an electron there around the oxygen, and it's going to be a little bit less likely to find it at the hydrogens. As a result, it tells us that you're going to have a buildup of negative charge here because it's more likely that you'll find electrons around the oxygen and then around the hydrogen. And that will make the water molecule polar. So this is a very useful thing to know because it explains the properties of water. Water's got a negative end, the oxygen end, that sticks to positive things, and it's got a positive end, the hydrogen end, that sticks to negative things. And we can understand how water behaves then in chemical reactions. So, to sum up, when you square the wave function, it gives you the probability of locating an electron. You can plot the square of this in 3 dimensions, or in slices like this as a 2-dimensional slice through a water molecule, and it will give you a map. This is called an electron density map. And it's really showing you where all the negative charge is building up. If these are like altitude lines on a topographic map, where it's highest is going to be where there's the most negative charge. And that's how you interpret the wave function. Now, another thing to notice is that when you have a node, there's a 0 probability of locating the electron there. And when you have more nodes, let's go back and look at the wave functions for the electron on a wire again. When you've got a node, there's a 0 probability of finding the electron there. This wave function with n equals 3 has got 4 nodes, 2 at the end and 2 in the middle, and there's a 0 probability of finding the electron there. This one has 3 nodes. There's always 2 at the end, and then there's only 1 in the center. There's no probability of finding the electron there when you're in this state, n equals 2. And you only have the end nodes when you're down in the bottom state. But notice that when I look at the nodes, the more nodes that I've got in the wave function, the more energy the wave function has got. In math, you look at something called a second derivative of the wave function, and that gives you the energy. And in English, saying the second derivative, the higher the second derivative, the more energy it's got. In English, that would be the curvier the wave function is, the more energy it's got. This is a curlier wave function. And what makes the wave function curvier? More nodes. So I'm going to write a little rule here that you can use to decide which wave has got more energy. More nodes gives you more energy. This is something to remember and something that we'll talk about quite a lot in the next lesson.